The steady state single flow process. An expression can be derived for the work in a steady state single flow process that shows how the significance variable influences the work output. We have noted that when a steady state process involves a single flow of fluid into and out of a control volume, the first law was obtained as this relation. And the second law we have SI plus S generation plus which will write in a differential form as in a differential form and we can calculate that delta Q part function TdS minus T delta S generation part function also. To facilitate the integration and find Q, we use the property relation and get this equation as TH minus T delta S generation. And we can obtain Q as this expression from I to E as function, which is equals to dH T delta S generation. And equals to H E minus H I minus T delta S generation. This result is substituted into the energy equation which we solve for work, which was Q HE This is Q, and also we have with simplification we can obtain this relation for work. Several comments for this expression are in order. The first one, we know that the last term always subtracts. T greater than 0 and we get the maximum work out for a reversible process where this term is 0. This is identical to the conclusion for boundary work. This equation, we do not write this equation because where it was concluded that any entropy generation reduces the work output. We do not write this equation because we accept to calculate the last energy for a process, but we show in to illustrate the effect of an entropy generation. Just second. For a reversible process, the shaft work is associated with change in pressure. Kinetic energy or potential energy either individually or combination. When the pressure increases, works tend to be negative. Work tend to be decreased. Negative. We must have sharp working. And when the pressure decreases, the work tends to be positive. Decrease. The work tends to positive. Pressure increase. More decrease. Pressure decrease, work increase. The third one is the control volume does not have a shaft work. Then the right hand side of the equation. The equation W equals to PI. The right hand side of the equation must be balanced out to 0. Any change in one of the terms must be accompanied by a net change of opposite sign in other terms, and notice that the last term can only be subtracted. So then we have this relation 0 As an example, let us briefly look at a pipe flow with no change in kinetic or potential energy. If the flow is considered reversible, then the last term is 0. For reversible process, this term also is 0, and the first term must be 0 also. That is, the pressure must be constant. With no change in kinetic and potential energy. And reversible process, the equation is constant. Realizing the flow has some friction and is therefore irreversible, the first flow term must be positive to balance out the last term. As mentioned in the comment above, the equations for the steady state process is useful to illustrate the work involved in a large class of flow processes such as turbines, compressor, and pump. Turbines for turbines, compressor, and pumps. In which change in the kinetic and potential energy of the working flow are small. The model process for this machine is also reversible. A steady state process with no change in kinetic or potential energy. The process is often also adiabatic. This expression reduced to VdP. From this result, we conclude that a steady state reversible Ke and Pe equals to 0 for pumps, turbines, and compressor. We have this relation. VdP. From this result, we conclude that the shaft work associated with this type of process is given the area of the PV diagram. For example, the area between the P-axis and the diagram of PV. This is work. It is important to note that these results applies to a very specific situation of a flow device and is very different from the boundary type works. PDV. It was also mentioned in the comments that the shaft work involved in this type of process is closely related to the specific volume of the fluid during the process. To amplify this point further, consider the simple steam power plant as shown in the picture here. Suppose that this is a set of ideal components with no pressure drop in the piping, the boiler or the condenser as shown in the picture. Thus the pressure increase in the pump is equal to the pressure decrease in the turbine. Ideal complement. Which no pressure drops in the piping. The boiler or the condenser. We have this relation. The pressure drop in the turbine is equal to pressure increase in the pump. The electric, kinetic, and potential energy change. The work done on each of these processes can be expressed as VdP. Since the pump handles liquids which has a very small specific volume compared to that of the vapor that follows through the turbine, the power input to the pump is much less than the power output of the turbine. The difference is the net power output of the power plant. The same line of reasoning can be applied qualitatively to actual devices that involve a steady process, even though the processes are not exactly reversible and adiabatic. A simplified version of the equation is incompressible flow W, the first term is 0, the first term is V constant, conversible and reversible. This is exactly which is called the extended Bernoulli equation. After Daniel Bernoulli, who wrote the equation for the zero-word term, which then can be read as the relation for V V. From this equation, it follows that the sum of the flow works, kinetic energy and potential energy is constant along a flow line. For instance, as the flow goes up, there is a corresponding reduction in kinetic energy or pressure. As final application for the relation of natural volume generation. We recall the reversible polytropic process. For an ideal gas. Discussed in the previous section, for a control mass for the steady state process with no change in kinetic and potential energy, we have this for PE W or W equals if the process is isothermal for N, note that PV and TS diagram for applicable for this relation to represent the slope of polytropic process. This evaluation of integrals may also be used in conjunction with the previous relation, the main relation, because in which kinetical and potential energy are not negligibly small. The principle of increase of entropy. The next section.